So welcome to video 1 in G03, our course on read mapping. Today we're going to look at why we want to map read libraries to reference genomes or reference databases. So what we're looking at when we were thinking about de novo assembly is creating a reference genome from short reads or long reads to create a full genome sequence. What we can do with our existing read sets, if we have a closely related reference genome, is map these reads to an assembly. We assume that our sample of interest that we're mapping reads from is reasonably similar to this reference genome. And the key step is that we have to align these reads to the reference genome and find the location where they best are aligned, if at all. And we can think that we have some long reference genome here, and we have these short reads that we're mapping to this genome, and that's the kind of process we're going to describe further. If we look in detail, we can think about this blue reference genome, and we're going to map reads to it. And you can see that this first read maps well at this place because it has no mismatches at any base here. And we can continue that process of read mapping for all the different reads and try to get a sense of what the sequence of this sample is. And that's the next step when we look in course G04 is to identify instances where there might be a base difference between our mapped reads that's consistent across all of them compared to the reference genome. And that would depend on the coverage, in depth, and the read quality. So we can map reads if we have a closely related reference genome. If we don't have a closely related reference genome, that process may be less reliable. So that's an important, and it depends on the diversity of the reference genome as well as not just the genetic distance, it's the level of resolution of the reference genome is important. So ideally, we expect just a few mutations occur to this reference genome, and therefore we can tackle the same goals as we would do de novo assembly, looking at how outbreaks originated, to look at transmission events between different specimens, and to look at things like gene expression results. So a lot of this links to transcriptomics as well. And our central problem with read mapping is the same as usual, that a lot of the genomes we deal with, even if they're very, very short, can be repetitive. So there can be small repeats that occur in the genomes, and therefore, if we're mapping reads from one sample to another, we have to just bear that in mind, that there'll be some small differences between the genomes, and those structural changes can mean that reads map in an unexpected manner. And then there's the technical artifacts as well, that we have the library prep steps. We would have QC'd our libraries already, ideally, but then there's going to be repeats, regions where maybe we have low coverage, home and polymers, other features that will affect our quality. And that's written about well in this article, that all of those potential things like oxidative damage, polymerase stuttering, base changes that occur during sequencing, all of which can lead to mistakes. And we want to eliminate those mistakes. We can better characterize the genetic diversity in our sample. And as mentioned previously before, we can quantify these errors reasonably robustly. So if we're dealing with older MiSeq data, our error rate of about 0.5% for any base in a read is a kind of a starting point for understanding what the error rate might be. And we know with newer technologies that error rate will be somewhat smaller. So that's the end of this first video on why we want to map reference genomes to map read libraries to reference genomes. Please see the next video on read mapping theory.